recording. Okay, so we have produced also a formula for so-called nth term of arithmetic sequence. So if you have first term, then second term, and so forth, so they basically continue infinitely, then adding d to every next term again and again and again, so just keep moving by the same exact number, will produce the following terms with their formulas. So if my very first term is called a, then to get to the next term, I just added that difference, or so-called d here. And then if I add d once again, and once again, I will produce the next terms. The observation made was the following, that to get to the second term, I add 1d. So if I was going to add for the second term, there was just 1d. So one less. And that's how the formula they have here in the gold box arises. So we take the very first term and add one less d than we need the term. So it's because first term, you don't add any d's. So it's n minus 1 here. And with this formula, it'd be convenient to get those following terms, of course. And that's what they actually show here in the example. So they say, as long as you know the difference d, and let's say it's -7, and if you also know the first term of your sequence, and looks like here they say 4, so that's a1, then you can find any term of it, such as a 8th term, and to find it using this formula, I'm going to utilize 4 instead of a1, and -7 instead of d. And also, I'm going to have to use the 8th term, so n will be 8. So I'm going to put 8 minus 1 in the parentheses, and then see what will come out. So it looks like I'll be adding 4 with a product of 7 and -7. And this is going to be minus 49, right? When I added those 4, I will get -45. So we have this formula in use. So why the formula is so good? Well, because you don't have to find any intermediate terms to get to that 8th term in a sequence. In fact, here they show you that technically you could start with the first term, and then -7 you get the next, and another -7 you get the next, and keep subtracting 7 or adding -7, right? But since you need 8 terms, you have to do this 8 times. And it is possible to do, but if they ask you for larger size terms, say 100th term, then doing this 100 times seem to be a waste of time. It's much faster to just use the formula. And that's actually the point of this whole process. So you want to use formula whenever you have this 8s or whatever numbered term to be found. So we also had a little quiz last time, remember? Let me find it. I think it should be among the exercises at the end. Do you remember what problem I asked you to do? Is it like exercise number 2? I think so. 2 looks familiar. Please correct me if I'm wrong. The last time, I think we had for quiz exercise number 2. So let me write first 6 terms of that sequence. So if you start with 5, that's your first term. Then to get to the next term, I just add 3. So that'd be 8. And then I keep doing this again and again. So I get 11, then we get 14. So there are already 4 of them, right? And 17 and 20. So we produced 6 terms. It's not really that bad, right? So it looks like we have special type of sequences they called arithmetic. And to get what from one term to the other term, you add same number. So just keep adding that so-called difference in between terms. This difference may be positive, this difference may be negative. So if difference is negative, so you actually subtract. But again, you keep moving by exactly the same number, whether it's positive or negative, but it's still the same. And that's how we describe this arithmetic sequences. So let's try another exercise here, maybe problem number 24, that will actually use the formula that I just talked about, the formula for the nth term here. It says an is equal to the first term plus n minus 1 multiplied by the difference, right? The formula of the nth term. So let me try some big one, like 27. A200. Let's try to find what A200 is. And this is going to be a pure formula exercise. We don't want to start with -40 and start to add 5 200 times to it. What we want to do is use in the formula numbers -40 for A1 and D, which is 5, right? So just place those numbers in. And instead of n, I put 200 because it's a term number 200 that I have to find. So I'm going to add these, and in the parentheses will be 200 minus 1, just like that, and calculate this result. And I guess the calculator will definitely be a helpful tool here. So let me use a calculator. So I'm going to put a -40 plus. So you could just enter your entire expression the way you see it, parentheses, 200 minus 1. Calculator doesn't care what you enter in it. It'll just calculate times 5. So 955. That's my answer. So when you have a formula, then definitely the exercises turn out to be very, very straightforward. But definitely calculator will be a big help. So we saw this arithmetic sequences. And again, to get from one term to the other, you just have to move by exact same value. So if you want, you can do the print screen of this page. Those are exercises related to this. And I would say, since there are so many exercises that keep asking you for the same exact thing, then maybe you don't have to do so many, maybe a couple of problems here. If you do them right, it's already good enough. So, well, I guess here we're not to prove these formulas. We have formulas and we just to use them. So you don't have to memorize or really get into this formula, but just use it. So instead of first term, you put one number, instead of n, you put the other number, instead of d, you put the third number, and then get the result. And I try to justify the formula, but if you don't like it, that's fine. You don't have to memorize or really get into much of details of it, because I'm not going to be testing on it. Let me do another one. Let me do number 37, just to show how we are using it. So in exercise 37, I'm going to be looking for A12. So this means that n is equal to 12. A1 is 6, and d is equal to 1/2. D is 1/2. So all they want you to do is put numbers in the formula. Once you have formula, you don't have to every time think how it was proved or how it all works. All you do is just plug in the numbers, and that's really all we need for this exercises. So instead of A1, I'm going to use 6, so I'll put 6 here. 6 plus, instead of n, I'm going to use number 12. So 12, so it'll be in parentheses, and I have to put parentheses 12, then minus 1, so I just wrote this term, n minus 1, so it's 12 minus 1, times, and now whatever we have here for a d, and d is 1/2. So this is it. That's all you need for the formula of the n's term. And now we're going to find the answer for it. So I'll put it in the calculator and get the answer. So the message is, when you have a formula, then you just use it. You don't have to every time think through it, what all that means or some other stuff. They just give you some random numbers, and you just want to put them in your formula like that, times it by 1/2 or 0.5, and you get yourself the answer. Because the nice thing of all these exercises is that you will be given that formula. Okay? So here it is. So I would say that's nice thing to have, because if you don't have formula, then every time you do these problems, you will have to produce the formula. And that's a little bit annoying. So last time I actually shown you how to produce this formula. I can produce it again. I'm sure that's a fun thing to do. So I can take a look at this. I guess I need some room for that. So first term, A1, then second term, A2, next is A3. That's our sequence, right? Arithmetic sequence, A4, A5, and so forth. So you could just continue. So how do we get those terms? We add D here, we add D here, and keep adding the same exact number called D. It's D. It's not A, it's D. But I just write it a little bit more. Difference. So keep adding this difference, D. And so forth. So I just keep adding the same D. And the whole point here is that to get to the second term, I don't add 2 D's. I add 2 minus 1 D's. Because I just add 1. To get to the third term, I add not 3, but 3 minus 1. 2 D's. To get to the fourth term, I add 4 minus 1 D's. Why is that? Well, here I added 1 D. To get to the next term, to A3, I added D once, and then I added D once again, so I added 2 D's. 2 D. That's my third term. That's how I get it. I start with the first, and I add 2 D's, and that's what I wrote here. So to get to the fourth, how many D's did I add? 3, right? Because it looks like I add 1 D to get to A2, get another D to A3, and add another one to get to A4. So observation here is the following, that when you need to get your following term, the number of D's you add is 1 less. So if that's 4, it's 4 minus 1. If it's 3, it's 3 minus 1. So if it's n, it's n minus 1. And that's really all it is. That's your formula. I just need to be careful because I put a plus sign. It's actually put equal. It has to be plus. I was not careful. Get this eraser real quick. It's plus. 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 Right? So that's our little formula. So, and again, you don't really have to understand it. You just use it. So get formula, we use it. In fact, I'm sure you took some other classes that had various formulas, especially if you take science classes, some physics, chemistry, they'll give you a formula, they just say memorize it. They're not even trying to explain how come they came up with this formula. They say, oh, from experiments, right? So just use their formulas and that's it. So I guess that's what all formulas are for. But yes, it's definitely a good idea to be able to see what these formulas all mean. But I guess that's the little explanation of what's going on behind when we trying to construct this little form. So anyways, it's here. So if you want to think about this more, you can watch this. Again, I'll send you the link to this little lecture, of course. So anyways, let me go back to the textbook and notice there is one more story that they have here. And they're talking about so-called formula for a general term, like in exercise number 41. Take a look at this exercise. So it looks like they once again want me to come up with this little formula. So A1 plus D minus, so n minus 1 times D. So that's the formula I just worked with. And now they want to pull out 3 pieces of information. First is A1. Second is the difference. And using them, come up with that formula for exercise 41. So what is the first term here? We say, Alex, what sits in the first place? That's your first term. Yes, indeed, that's going to be number 1 because we start with that number. Okay, so what's the difference? How do you move from first term to the second? Wouldn't you add number 4? Looks like, well, let's check it out. What if you move from 5 to 9. Would you again add 4? Yes. And from 9 to 13, you'll add it once again. So for exercise number 41, then I can write down the formula for the nth term. I just need to replace my A1 with a number 1, right? Plus, now n minus 1, I keep the way it is, and I just plug a difference 4 in here. So I just put instead of A1 and instead of difference, the two numbers. When I say, Alex, I want to simplify this because I learned that we always simplify. Because if I have some parentheses, then definitely 4 could be distributed, right? Well, let me distribute and see what will come out. So I have 1 here plus 4 times n and minus 4. So the actual formula that we produce will look like that, 4n minus 3. This is better because if you want to calculate something, it's easier just to plug the number in instead of number in whatever term you are looking for, and you'll get the answer right away. So it looks like if you are given this first term and the difference, then everything is fine. And that's what this little set of exercises is talking about. Well, turns out that they have another sequence called geometric sequence, which is different with the arithmetic sequence in this same section. So let me introduce you with those geometric sequences as well. So that's totally different type of sequence, and the terms you produce not by addition, but by multiplication. And here they give some examples of the sequences that you have produced by multiplication. For example, figure 517 shows that we multiply by some fractional part. Looks like we divide by 9 and we multiply by 5. So we actually times by 9/5. Multiply, so put times, not add, by 9/5. I say that's kind of odd. Well, yeah, you break it into 9 pieces, 3, 3, and 3, and then they just take 5 of them, of this little 9 pieces. You see how it works? That's kind of interesting to observe. So I noticed that I break the first one into 9 pieces, and then I select this piece, this piece, this piece, and that, and that. 5. So, oh, 5 9s, sorry, I should be 5 out of this 9 pieces. So rewrite it. So, move from here to here, I divide it by 9, and then take 5 pieces. So I multiply by 9/5. And then I do the same thing with each of these little squares. So each square I divide by 9 and take 5 of them. So again, I multiply by 9/5 every single one of them. If this is 0, then there is nothing. But if there is 1, then we have 9/5 of each of them. It's interesting to think about, right? So it looks like this type of pattern appears in, say, snowflakes, right? Looks like this is one like snowflakes. So what they do here is they trying to convince you that these geometric sequences are around us, and that's absolutely correct. So geometric sequence you produce by not adding the same number, but just keep on multiplying by so-called common ratio. And here are some examples of geometric sequences that you can see here on the bottom of page. I just want to look at their examples. They produce very nice ones, I think. Say, first one says, you start with 1. So your first term is 1, A1. And then you times it by 5. You see, you multiply by 5, you get 5. Multiply by 5 again, you get 25. Again, 125. And so forth. You keep multiplying by 5, so your ratio is 5. For the second one, we have first term, which is 4. First term is always pretty straightforward to find, right? Just take the first number. And the ratio, well, you need to multiply by 2. You need to double. Every next step, you just multiply by 2. So you just keep on double. So ratio is 2. The next one is a little bit different. Notice that signs go from minus to plus and so forth. So they alternate. So it looks like you do double, you do multiply by 2, so you get 12, but you actually multiply by -2. So when you multiply 6 by -2, you get -12. But when you multiply it again by -2, you get +24. Again, by -2 is -48. Then by -2, it will be +96. So since your ratio is negative, the signs will keep changing from plus to minus and so forth. And analogous is the last example here. So it looks like here I divide, not multiply, because when I divide 9 by 3, I get 3. But actually you divide it by negative. So instead of dividing by 3, I can say I times it by -1/3. So I take 1/3 of it. And if you take again 1/3 of it, so you'll divide by 3, you get 1, and the negative sign will turn positive. And again negative, and then again positive, and so forth. So it looks like this last geometric sequence will deal with a bunch of fractions. So next term will be what? -1 over, looks like 3 times 9 will be 27, right? And then so forth. So +1 over 81. So just keep on multiplying those terms. So instead of adding, we multiply. Geometric sequence. Okay, so they write various terms of this sequence and also coming up with the formula for the nth term. So let me say a couple of words about this formula. I just want to get some room for this. So how do we produce so-called nth term of this sequence? Well, analogously to the previous example with the formula for the arithmetic sequence, notice that my first term is A1. That's always the same. Now to get to the next term, I multiply it by R. I say, why not difference? Well, they like to use word ratio to just associate with geometric sequence to better show that we're actually multiplying here, not adding, but multiply. So they talk about the ratio. So let me write these formulas. So A2 is going to be A1 times ratio. A3 will be multiplying this by ratio again, so it'll be A1 times ratio, so it'll be ratio squared. Please notice that the way I move from term to term of this sequence, I just multiply by R times R. Here again, I times R. So when I times by R, it'll be R times another R, it's R squared. And then I times by R again, it'll be R cubed. By R again, R to the power of 4, and etc. So looks like for the nth term, I'm going to take my first term, A1, and multiply it by R raised to the power 1 less, N minus 1. Because with 3, I have 2, right? With A4, I'm going to have 3. So we have 1 less. And that's exactly what they have here, the formula for the nth term. Again, don't have to get really deeply into this story, but the formula is what we should be familiar with and use it to do the exercises. So let me get this formula in use. So I'm going to the section end, and let's do some problems here in the next group of exercises that talks about geometric sequences. So that's the next group. So I guess for homework, you just need to worry about first page here, because the next page already has practice plus stories. So there's some actually a little bit more on the next page. But I think first page should be good enough. So here. So geometric sequence formula right now. So geometric sequence formula. So let me try first exercise like 49. Let me do this first 6 terms right off for problem 49. Okay, so I'm going to be taking first term, which is 4, and then I times it by 2. So what would be the next term? 8, right? Multiply by 2. Again, multiply by 2 is 16. Multiply by 2 is 32. Looks like those are familiar numbers. 64. Nowadays, I already wrote 5 of them. So one more will be 128. And yes, for homework, you can do problems on this page. So that should be good enough, I think. So, well, let's do it again. Let's try one with negatives. How about 61? Exercise 61 with negatives. Well, with negatives, we're going to have sign alternating terms. So once again, I list my first one, -6. And then again, it's a geometric sequence. So I'll be multiplying these negatives. So I'll be multiplying -6 by -5, right? Would that be 30? Because ratio is -5. So I'll keep multiplying by -5, all of these terms. So I'm going to be getting the next term, it's 5 times 3, 15. So that'll be -150. You say, oh, that's getting bigger. Yeah. And the sign changes. You see that? So now I multiply by 5 again. So 5 15ths is 75. And the sign will now be positive. So you get 750. So you say, Alex, maybe you should use calculator to make sure that this is done correctly. I think it's a good idea. So let me multiply 750 by 5. I say by -5. We can multiply by -5. Calculator doesn't care, just put -5 here. And looks like the next term will be pretty big. It's going to be -3750, right? So I already have 5 of these guys. I need one more. So let me multiply that -3750 by 5, right? And then we'll be done. Fine. So times this by -5. It's going to be positive 18,000. Do you see that number? 750. So I think this is a good example that shows that geometric sequence has terms that very rapidly increase. If you're working with arithmetic sequence, when you just added numbers, well, they little by the same step, they increase. But with geometric, look at this, it's 5 times bigger. From 6, you get to 30, and then to already 150, and then almost to 1,000. Then you deal with 3,000 and with 18,000. The next term, well, you can just think of how large that'd be. Probably close to 100,000, even larger than that, right? So you get to millions very, very rapidly. So the geometric sequences, they increase very fast, but they can also decrease very fast if your ratio is small. For example, let me try exercise number 70 here. One more problem, exercise 70. So it talks about working with first term is -1,000. So that's my first term. Let me write it. And the ratio is going to be 0.1. Ratio is positive, so all my terms will be positive. Oh, will be negative, sorry. So I just keep multiplying that negative by positive, again by positive, so just keep getting negatives. And when I multiply by 0.1, instead of 1,000, I'm going to get 100. Notice that negative sign will stay, but I basically divided by 10. Times 1/10 means you divide by 10. So if I divide by 10 again, I'm going to get -10. See? If I divide by 10, so I drop in 0, we get -1. What's next? Well, I multiply it by 0.1, so it'll be -0.1. Okay? That's already the 5th number. So one more. Well, if you times it by 0.1, it'll be -0.01. Just like that. So you keep producing the next terms by multiplying. And of course, you want to make sure you keep track of the sign, if it's a plus or minus. That's important. Because sometimes it changes, sometimes it stays the same. So in the next exercise set is similar to what we saw here already for the arithmetic sequences, is producing the nth term. Like in the problem number 71, they tell me A7 is what they want to find. A7. So n is equal to 7, because that's the nth term formula. Notice the resemblance. Once you are using the formula, you just need to see where to plug your numbers instead of what. So instead of n, I'll use 7. Okay, my first term will be 4, and the ratio is 2. Okay, so instead of first term, I put 4, right? Then it's multiplied. No operation means times. It's multiplied. And the ratio is 2, and it's raised to the power of 7 minus 1. So n minus 1, I put 7 minus 1. And calculate. So it looks like I multiply 4 by 2 to the power of 6. And why don't I just use a calculator? Because these terms might be pretty large. So let's multiply 4, right? By 2 to the power of 6. 256. So advice is, yes, use calculator for these problems, because otherwise it's so easy to make a mistake here. So don't make mistake, use calculator. So please notice when I use this formula, I don't really care how it appeared. I just have a formula, I plug in the numbers, and that's standard for all exercises that use formulas. Let me find some big term, let's say 75, A100. Can you just guess what this A100 is? I think that's an interesting question. Look at the ratio. it's 1, right? So you keep multiplying by 1, and this doesn't change anything. So it looks like it's just going to be number 50, right? Because you have ratio equal to 1, so you just multiply by 1, and then again by 1, and then again by 1. When I multiply 50 by 1, I get 50. Again by 1, I get 50. Again by 1, I get 50. It looks like this geometric series is pretty unusual. It's just 50, 50, 50, 50. So terms stay the same simply because ratio is 1. I say, what if I use formula, Alex? Will I get the same answer? Oh yeah, you better get the same answer. So n is 100, so it'll be a 100th term that I need to find. And I utilize 50 for my ratio, right? And I times this by 50 for first term, sorry. First term, ratio is 1 raised to the power of 100 minus 1. Minus 1, right? Which is 99. So you can put this in a calculator and get the answer, which is better be 50, right? It's better be 50. So let me check it out. 50 times 1 raised to the power of 100 minus 1 or 99. And yes, indeed it is 50. Of course it is. Yeah, I found unusual question, one may say. Well, it doesn't really matter for us. It's as long as you have the answer, then you got the result. So let me try one more and then you may try one, right? So how about if I try something with a negative ratio? How about problem number 80? Well, -1 is not interesting, maybe 81. Let's try negative ratio. So an exercise number 81. Our ratio will be -3. And I need to find a 6th term. So I already know that n will be 6, right? N is the index of the term. Well, let's see what term number you need to find. So once again, I'm looking up here. This is the only formula that we're utilizing. So we're going to have to put instead of A1, the number they gave us here, it is -2. You see it? And then times this by ratio, which is -3. And this is raised to the power of 7. You see that? N minus 1, so it'd be 7 minus 1. 7 minus 1 is 6. So you have -2 multiplied by -3 power of 6. See, you definitely should put this in a calculator because that'd be a mess if you try to do this by hand. So we have, again, -2. I just enter them the way they are. Parentheses, when I multiply by negative, I always put parentheses. -3 is here in the parentheses. And then here's the power symbol, power, and we have 6. And here it is. Whatever the answer is, I just recorded 1458. Just like that. 1458. So there's two kinds of sequences, arithmetic and geometric sequences are utilized in this chapter. And sometimes in the real life situations, you encounter those, and that's why they actually talking about this. For example, let me take a look at example so we can see where it's used. The population grows. So population is just keeps on increasing geometrically. So here's one of the examples. So you start someplace and then you get more people and more people and more, and right. And that's how they treated. They say the ratio is here, 1009. So if you multiply by 1009, you get bigger number. So every year you get an estimate for population size if you times the previous year by 1009. So this way it just keeps on increasing. It's always going to increase. So that's how population grows. And that's really geometric sequence we have here. So it's really useful in various areas of science. When they say bacteria grows, so bacteria also grows in geometric sequence. There is a so-called half-life. It's like radioactive decay. So if you encountered those nuclear reactions story ever, it just that radioactive stuff just keeps on decaying every year by the same amount, less. So it's the same ratio involved. So it turns out that in nature or in the real life around us, these geometric sequences are quite popular when something is decreasing or increasing with the same ratio. We can eventually see what we get at the end. So let's have a little quiz on this. How do you feel about these geometric sequences? I'll give you something pretty straightforward, like exercise number. In question 81, the ratio, let me see, let me double check that. Go back to 81. So 81 is here, right? So let's double check. So in problem 81, we have n is equal to 6. Oh, you're saying that I miswrote, I wrote A7. Yeah, you're right. I used 7, but it should be 6. It should be 6. You're absolutely right. See, you already know this better than I. That's the very impressive. So yeah, if that's a 6, A6 is what I need to find. See, I found A7. I wasn't careful. I found A7. Why did I find A7? I don't know. I guess I like 7. But you're right. This problem actually asks for A6. So maybe you can try to find A6. Maybe it'd be a good question for a quiz, by the way. What do you think? So I just found A7. So I put this A7. So can you find A6? Just look at what I did to find A7. You're right, that's not A6, it's A7. And tell me, what is A6 then? That could be a good quiz question. Thank you for giving me a great idea. Thank you. So again, look at the, actually do problem 81. That's gonna be our quiz exercise, right? I just did pretty much same thing, but I found A7. But I didn't really do 81 because it says A6. So please try to find A6 then, and that'd be our quiz for today. And stop doing this recording.